Today we're going to start Chapter 7. We're in particular going to take a look at Section 7.1, which is an introduction to finite decimals. The first bit of language or vocabulary that we're going to take a look at is the word decimal. The word decimal comes from the Latin word meaning 10. A bit of vocabulary in terms of place values. So we're not going to list everything because that doesn't even make sense to try, but we're going to list out several place values. So I'm going to do 2 before the decimal point and we're going to do 6 after. Okay, they're not all straight, but pretend like they are. So if we are to the left of the decimal place, this is the tens place, and this is the ones place, also sometimes called the units place. Okay? As we move on, we actually sort of reverse the ordering of what's going on. So this is the tenths place. It's got that THS on the end. This is the hundredths place. We have the thousandth place. So what do you suppose comes after tenths, hundredths, thousandths? 10,000ths, you bet. So we have the 10,000ths place. And then what do you think it would be? 100,000ths. And what do you think the next one would be on my screen? Millionths. And we could keep going. For the purposes of our discussion, that's probably far enough. But we can keep going with the same pattern, right? It would be 10 millionths, 100 millionths, and then we would have billions. And then we had 10 billions and 100 billions, and then we would have trillionths and so forth, and we could continue to go. So what we're going to do first is we're going to talk about how we rewrite or how we would actually properly say a decimal in its form. Because believe it or not, this is not 32.4236. No matter how many times I say it that way or you say it that way. That's really not how you're supposed to say it, right? It isn't. And so you might be sort of thinking, I do my best to try and tell you where I see this being used in sort of grades as we go along. It's one of the benefits of being a mom of kids in these grades right now. So you're looking at this in about 4th to 5th grade and being able to use language out at least this far. So obviously simplified, decimal points and simplified whole numbers and stuff before that. But we're going to start with this one. So we're going to say 32. There is a hyphen between the 30 and the 2. I don't get too all up in arms if you forget your hyphens. I'll just put them in there for you. But a decimal point is read as the word and. I have very specific memories from 2nd grade about saying things with the word and in the middle of them that shouldn't. I don't know if you had teachers that did that to you, but I did. And so she would say, "Oh, you can't put the word and in." I'm like, why isn't 425? It just isn't. Well, it isn't because the word and for us in mathematics is designating that decimal point. All right, what we do next is we say all of this as though it were just 4, 2, 3, 6 with a comma right there, okay? So how would I say this number if it weren't in the place of the decimal and so forth? I would say 4,000. Then what? 200. What's next? 36. And again, the 30-6, like that. And then what we will do is we will actually indicate the place that it's located in. So if you do this based on the very last decimal point, non-zero. Okay, if there were some zeros trailing at the end, we would ignore them. The last decimal place right here that's got a number that's not 0 in it. And what place are we in? Well, we can kind of tick it off and count it, right? This is the tenths, hundredths, thousandths, so we're in the 10 thousandths place. And that's the last thing we would write down. I don't have enough space, so I'm just going to write it underneath that. This would be 10 thousandths. That's how we would actually say that correctly. Okay? It's kind of like one of those grammar things, right? You guys always say something wrong, and sometimes you even remember it and you know it's wrong, but it's just ingrained in you and you still do it. I'm talking about, right? This is one of those things too. This is the correct, if you will, mathematically grammatical way to say this particular number. And we want to be able to go the other direction as well. That is to say, we want to be able to take something that is written out in language and turn it back into the numerical or the number form of the value. So this one says 536 and 76 thousandths. So our first kicker would probably be to identify the word and, because it separates it with the decimal point. So we have this piece, and then I have a decimal point, and then I have this piece. So here's my decimal point. 536 would be 536, and then we have a decimal point. And then it says 76 thousandths. So how many places over am I going to need to end with the number 76? 3, right? I know 76 is only 2 digits. I get that. But it's supposed to be in the thousandths place. So there needs to be 3 digits here. And the 76 has to end in the 3rd place. So there is a 0 in here that's sort of hidden, right? At least in terms of the language part of it. We don't hear it being said, but it is there. So this is how that number would look, of course, minus all the weird spacing and the lines underneath it, okay? So something like that. All right, we're going to take a look with that same idea of those lines that we did a moment ago at base 10 numerals. So I want you to write three of those lines, put a decimal point, and then we'll do 3 more lines. Okay, so a moment ago I wrote words underneath them, okay? We're just going to write the place value in a numerical form, like a number form, okay? So this is the hundreds place, so we're going to write 100. This is the tens place, so we're going to write a 10, and this is the ones place, so we're going to write a 1. Now I know the next place value is the 10th place, and I know it has a decimal form, but 1/10 as a fraction would look like this. Does that make sense? And the next one is the hundredths place, so 1/100th as a fraction would look like this. And we have the thousandths place, it's 1/1000th as a fraction. That's what the value of those place values are. So when you're looking at, a dime and you're in this place, it's because a dime is worth 1/10 of a dollar bill. And if you're looking at values in this place, you're looking at values like pennies that are 1/100th of the value of a dollar bill. There's a note down here at the bottom because I want you to be aware that your book does this. And I would prefer that you not, because I don't think it leads to the intuitive kind of approach that you would expect of your kids in your classroom. It doesn't lend itself well to understanding. It's sort of hidden in some sort of a cover when you're using it. Your book likes to use negative exponents, and so instead of writing 1/100, which is how I would prefer that you would write it, they would write it as 10 to the negative 2. So it has this sort of nice pattern to it, right? Because what I could do is I can write that this is 10 to the 0, and this is 10 to the 1, and this is 10 squared, and I can go the other direction, and this is 10 to the negative 1, and 10 to the negative 2. There's this wonderful sort of patterning in it, but I don't think that it leads to you feeling like you really know what that value means quite as well as the fractions. I know you're not super loving maybe fractions, but I think negative exponents on basis of 10 is even probably worse in terms of content conception knowledge. So when your book does those negative exponents, please just ignore them and understand I'm asking you to do it differently. Okay, this is one of those places where, very few places where I do something different than the book. So we're going to do an example, and we're going to write this number 103 3/100ths in expanded form. So expanded form means that we're going to write each number times its place value. So that 1 is in the 100ths place, so it's 1 times 100. It's kind of like you're actually like counting out bills, right? Like money. You have one $100 bill. I go ahead and put in the zero placeholders because I think it's helpful to see them. But if you leave the zero placeholders out, it's not wrong. There's 0 tens. And then there's 3 ones, so 3 times 1. And then I have 0 1/10ths. That would be like my dimes. And I have 3 100ths, and that would be like my pennies. So this is what expanded form would look like. Yes, there is. It may not be coming through from your angle, but it's there. Yeah. And if you don't like the dots, you're welcome to put parentheses around them if that helps you to sort of distinguish them differently or more clearly. That would be okay as well. You could do that. All right, there's a really good picture, and it kind of blends back into some of the images that we saw back in the fraction section. It's called a decimal square grid. A decimal square grid is a 10 by 10 grid. If it's 10 by 10, of course, it would contain 100 squares. I don't do a very good drawing of this. Yours will very likely be better than mine, but we're going to give it a go. So the idea is to create a square and to break it apart into 10 columns and 10 rows. All right, the more columns and the more rows you get, the more of a mess mine tend to look, so we'll see what happens. They should be equally spaced. Of course, mine will not be. Definitely one of my better grids. I'll give you that. Okay, and if the lines all went, to the bottoms and the edges and stuff, it would look a little bit cleaner, but it's not too bad of an idea. So this is my decimal square grid. And if I had my base 10 blocks, which I don't have today, I'll try and remember to bring them next time. Every time I come to this lesson, I forget to bring them to class. So we would have an image of this. I'm going to copy and paste this to the next page for myself. You're welcome to sort of just make yourself a note on your next page if you want to. See page before so you don't have to redraw it. But the question on example 4 asks me to draw a decimal square grid for the number 24 hundredths. So this is 100 little squares. So how many do you suppose that I will shade in? 24 of them, exactly. Please do some sort of organized way of shading them in. Don't just randomly shade in 24 little dots all over the whole screen, because that's going to make it really frustrating for the grader to grade. Right? So I can go with all of these, that's 10, all of these, that's 20, and then 4 more. I did mine horizontally. You could certainly do them vertically. Either way would work. If you want to use a highlighter or something like that, you're welcome to use some colors to do so, or you're welcome to shade with your pencil. So this would be a decimal square grid for the number 24 hundredths. Theorem 7.1 talks about how it is that we end up with decimals that are able to stop. So a rational number, a over b, in simplest form can be written as a terminating decimal, a decimal that stops, if and only if the prime factorization of the denominator contains only 2's and 5's. And this and is like an and or. So it could just be 2's, it could just be 5's, or it could be 2's and 5's. Okay, so anything else in the denominator from the simplest form version that it contains 3's, 7's, 13's, 17's, whatever, 33's, that's not a good example, 11's, how about that one? Any of those that it contains, it will not terminate. Okay, and we'll get into what that looks like in 7.3 when it happens to not terminate. We end up with repeating decimals, right? So we're going to mentally, on example 5, decide if numbers terminate. Now there is a really good awareness thing right here, is that this says we have to be in simplest form to make this decision. Sometimes you can forget to put it in simplest form and you'll get by. It'll still work out okay. Sometimes it won't. So putting it in simplest form is your best first option to always make sure that the rest of it flows properly. So taking a look at 9 over 24, is it in simplest form? No. What will the numerator and denominator both divide by? 3. And this is a very good example of one that if I didn't put it into simplest form, the fraction 9 over 24, that is a denominator of 24, would look like it doesn't terminate. So this gives me 3 over what? 8. Okay? How does 8 break down? Well, 4 and 2, and 4 is 2 and 2, so it breaks down into 2's. That's it, just 2's. So what this theorem says is if it breaks down into 2's, 5's, or 2's and 5's, which this one does, it will terminate. So the answer to that first part of this question is that it does terminate. Then it says, if it does terminate, find the decimal representation. So I am fully aware that your calculator can take 3 divided by 8 or 9 divided by 24 and spit you out an answer. I get that. And that's great for you to check it. In fact, I'd encourage you to, because otherwise, you're sort of not utilizing all your resources. But I expect to see what you would expect to see out of that 4th grader or that 5th grader, which is long division. Okay? So that would look like, again, you can do this, the reduced version of this. You do not need, I got that in the wrong spot, sorry. You can do the reduced version. You don't need to do the original one. So we've got 3 divided by 8. Of course, 8 does not go into 3, so we put a 0 up here, right? And so now I have a decimal point here. We would ask ourselves, how many times does 8 go into 30? 3 times. 3 times 8 is 24. If I subtract, what do I get? 6. So we're going to keep going until I get, the remainder of 0 at the bottom. That's how long I keep going. So now I've got 60. 8 goes into 60 how many times? More. 7. 7 times 8 is 56. If I subtract, what do I get? 4. So still have a remainder, so I'm going to bring another 0 down. 8 goes into 40 how many times? 5. 5 times 8 is 40. So once I get to a 0 here, this tells me to stop. And the answer is right there. 375 thousandths. Okay? It will stop. How do I know it will stop? Because there's only 2's in that denominator, right? So it's going to. And again, check with your calculator to make sure you didn't make a simple arithmetic mistake, of course. But this is the correct answer. 10 over 24. Does it reduce? It does. How will it reduce? Yep, you can divide both of them by 2. So 10 divided by 2 is? And 24 divided by 2 is? 12. Now let's factor 12. How does 12 factor? 3 and 4, and 4 is 2 and 2. So these are my factors. Will this terminate? No, it will not. Why? Because there's a 3 in the reduced simplified version of this fraction, right? And in the denominator. There's a 3 there. So this does not terminate. So do not get trigger happy and start dividing everything you see. If you do, you will end up doing divisions you don't need to do. For example, on this one it says, if so, write it as a terminating decimal. Well, there is no if so on this one because it's not a terminating decimal. So I don't have to do any division on this one. that make sense? Okay, so just slow yourself down because the tendency is, it said to divide, let's divide. Well, only sometimes, right? All right, we're going to look at comparing or ordering, putting decimals in order. So we do this by lining up the numbers by place value. And what that means for me is I put them vertically on top of each other so I can see them easier. We're going to read the numbers from left to right to find the first difference, that is the first place where they are different. And number 3 is that we're going to compare the different digits. So example 6 has these numbers. And if I were doing this problem on a piece of paper, I'd write all of them down, top to bottom. You actually have them sort of listed already on your paper, so I'm only going to write the last 3 underneath the first one. So I'm just going to rewrite. So this is 13.492. Got to be really careful that I can write small enough. I have 13, my decimal point, 49183. And then I have 13,49199. Now, I'd make them the same length. So everywhere that they're not already the same length, I'd just put in sort of, I don't like the word imaginary, but they're placeholder zeros. That's what they really are, is placeholder zeros. So they're all the same length. It's easier to compare them. So as I'm looking from left to right, so I've lined them up, that's step 1. I'm going to read them from left to right, and I'm looking for the place where they're different. Well, they all got a 1 in the tens place. They've all got a 3 in the ones place, and they've all got a 4 in the tenths place, and they've all got a 9 in the hundredths place. All that matches. So it's irrelevant to making a decision. The next place is where I actually see something different. So what do you see that's different in the thousandths place? There's a 2 in the second one. So what does that tell you about the number that I've just drawn my blue arrow to? It's the biggest, because 2 is bigger than 1. So this one right here is, I'm going to call it number 4, because we're ordering them from least to greatest, right? So this is number 4. It's the biggest. Now that I've decided that, I can sort of ignore it. It's irrelevant now. I already know what place value it goes in. So now I'm just looking at the other 3. So I've eliminated this one as a consideration. And in the next placeholder, the 10,000ths placeholder, what do you see? 9's the biggest, and there's only one that isn't a 9. It's this one, right? That one's got an 8 in the 10,000ths place. So this one's the smallest. So this is not option number 1. It is the first one of my list. And again, we've now eliminated this particular item for consideration. I only have the first one on my list and the last one on my list. Which one's bigger? The bottom one. How come, AK?
9's bigger than 0.
9's bigger than 0. You got it. So this one's bigger, which means that it's number 3, because we are going from smallest to biggest, meaning this is option number, or place value. It's the second one. I don't know what to call it now. Keep using different words. I don't know. All right, so what I need to do then is to write them from smallest to largest. So the smallest one was 13.49183. If you want, you can put a comma, or I kind of like putting my less than sign, because that actually, again, solidifies the fact that I'm going from smallest to largest. The second one, which is the first one I was given, 13.4919. The third one, which was 13.49199. And my last one, which is number 4, which was 13.492. Okay, any questions on that? Do you mean, why did we know that A terminated?
Yeah, like I don't understand why those like don't matter. Just like the 2's and the 5.
It's not that they don't matter, it's that things evenly divide by them. And the reason it works is because we have a base 10 system, and the number 10 divides by 2s and 5s. That's actually why it happens, is because our base system is a base 10 number system, and 10 is divisible by 2 and 5 and nothing else. So that's why we look over 2s and 5s. Good question. All right, one last question. What is the meaning of the word tithe, and how is it related to decimals? 10%. Any others? You'll usually not hear the word percent when you see it mentioned in the Bible. Do you know how it's referenced? They'll talk about it being the first, but there's something else in terms of the digits that I'm talking about. They like to refer to it as a tenth. Right? They don't actually use the word percent. These are equal wordings. I mean, they mean the same thing, but it's a tenth of something, whatever, So usually when we talk about it in terms of an evangelical Christian perspective, we're talking about a tenth of our increase or our income. So in practice, when it says, how is this related to decimals? In practice, we take 1/10 of our income and return it to God. And we do that via our local church. So every now and then you'll hear people say something like, well, I tithe 5%. You can give 5%, but you can't tithe 5% because tithe has an attached meaning to it, right? Or you might actually hear people say something like, I gave a double tithe. Well, you know what that means, right? It would mean they gave 20% of something. Or occasionally you'll hear somebody say something about reverse tithe. Reverse tithe would mean what, do you know? It would mean you kept 10% and you gave away 90%. For whatever the situation or context was. So those are some phrases occasionally you'll hear them say, but just a real quick example. I know you guys know how this works, but example, if you earned $50, you would give back how much? 5. That's how it works in practice. Directly related to our ideas of fractions and decimals.